Thank you. So this presentation will be more of a pitch than a scientific presentation. So we built this framework that we call SLAMBench. We've designed it for automating benchmarking for SLAM algorithms. And so it's open source. We really want you to use it. It was one of the options for the Lifelong SLAM Challenge for this workshop, for the challenge. And so I'll first introduce a little bit of the ideas and why we started to do it, and then some of the timeline. And I'll finish by sort of describing some of the things that we want to do in the future, and also we really want to collect feedback, and we really want to know what the community needs and the direction that we should be taking this framework towards. So benchmarking SLAM systems is difficult, and part of the reason it's difficult is that we need to deal with a really wide spectrum of tasks, sensors, different environments. So we're way past the origins of SLAM, which were essentially doing odometry. Nowadays we've been starting to integrate various other things. So there's 3D reconstruction, which isn't that new, but now we have semantic understanding, we have things like non-rigid reconstruction. Depth estimation has been making its way into SLAM systems. And we have a variety of sensors. We have so many different applications, from autonomous vehicles to robots to augmented reality. And so, given that we have such a wide spectrum of different things that we need to consider, in the end, we'll need to optimize our systems in order to work for a specific application. I don't really see a generalized SLAM system that would work anywhere and in sort of on any kind of platform and in any environment anytime soon. So SLAMBench started with the Pamela project, and the explicit aim of the Pamela project was bringing vision to sort of embedded devices and being able to do things like SLAM on mobile robots, on mobile phones. This was started in 2010, I believe. 2012, sorry. And it was a partnership between the University of Manchester, the University of Edinburgh, and Imperial College London. So the first version of SLAMBench and the beginning of it was, how can we optimize Kinect Fusion initially to be able to run on a variety of platforms, from mobile to desktops, and what do we need to do to get it to work on mobile? And so that's what we did in SLAMBench. We had multiple implementations of Kinect Fusion, so from just C++, OpenMP, OpenCL, CUDA as well, which we benchmarked on 3 different metrics, so speed, power, and accuracy. And we had a couple of scripts to run the system, collect data, analyze performance, so all of these. But importantly, we wanted to test it on different platforms and on different operating systems. And following this, Hypermapper was developed. So Hypermapper was another project inside Pamela. And the idea of Hypermapper was basically tuning parameters and finding the best configuration for a given device, a given platform. I wasn't involved in Hypermapper. I won't be able to give too many details about this, but I can point you to the right people. But in any case, part of this idea still stays with the project and the people who were involved, in that we're really looking for finding the really good configurations to run a certain system on a given platform, task, and so on. And so SLAMBench plus Hypermapper plus the new ideas I'll be presenting are going in this direction. And with Hypermapper, that was actually a really large project, and they ran it on like 80 different phones, and they found like some really good optimizations just by exploring the parameter space. So I really encourage you to check out the paper. The results are really good. So, what do we need in robotics now? One of the things that we need is we won't be having a generalized SLAM. Hopefully we won't be having just one SLAM system that everyone is using, because we really need this diversity given the diversity of our problems. And so something that's really important for us is being able to easily compare SLAM systems in a way, to quantify how well our SLAM systems are working for the specific cases that we care about. And there's a variety of things that we need to consider. So algorithms, dense, sparse, there are different methodologies in which we do SLAM. And again, the performance will vary depending on where we're going to apply them. We're going to have different sensors available, different environments. The hardware that we might perform the computation on is going to be different. One of the projects we're involved in now considers robots in nuclear environments, so there you have lots of restrictions in terms of how large can your robots be. You don't always have connection to the internet, so you won't be able to do your computation in the cloud. So you need to consider all those things. And then the question is, what metrics do we care about? For example, people who don't deal with robotics usually don't even consider power. And that's reflected in the fact that there are very, very few benchmarking systems where you can evaluate power as well. So, all in all, it takes a lot of time exploring all these things, and it's kind of painful. So what do we need in order to do these evaluations? We need a benchmark that doesn't care about how your algorithms are implemented. All it cares about is defining an interface, and as long as you respect that interface, then you should be able to evaluate your algorithm. It shouldn't be bound to one specific data set. So one of the things that I think all of us have experienced is that you have so many different data sets, and each of them has their own benchmarking, their own tools for integration, and it's usually like 2 weeks before the deadline and you're trying to squeeze out a few more results, and it's just getting all the different things working takes a lot of time. And it should be context agnostic, and by this what I mean is you should be able to run your algorithm and run the benchmark on whatever system is necessary, of course, as long as you have the requirements set by algorithm. So SLAMBench 2 was the next step, and what we did in SLAMBench 2 was now we introduced the option to run algorithms head-to-head on given data sets. So now we would be able to just say, I want to compare orb SLAM with, say, LSD SLAM on the TUM data set, and you build those algorithms, you build the TUM data set in a unified format, which is provided by SLAMBench. I'll show that in a minute as well. And then you'd be able to just click a button and compare them. And this gives you access to a really massive spectrum. So you have lots of algorithms that we've already integrated. I have a list at the end which I can show you, but you essentially just pull that off GitHub, you say make, and you have access to that. Quite a few data sets that we've also integrated, and it's all in a unified framework. So again, all you need to say is make TUM, and you have the data set. And then you have access to a couple of front ends and all the metrics associated with a specific problem. So I have a quick demo, and demos usually don't work, hopefully this time as well. Right, so this is Kinect Fusion running under SLAMBench on the ICL data set. That doesn't look great. Let's see if I can. I'll just try to modify the display so that it looks better. Well, in any case, you can see, so this is, as I said, this is Kinect Fusion running on the ICL dataset. There are a couple of things you can see. So firstly, you have, the input. This is a depth, RGB, reprojection of the reconstruction. You can move around, so you can see the ground truth pose and the current pose as it's building the model. You can also follow the align pose so that we can just turn off the so that's Kinect Fusion, and just the same way. So this was just saying pass Kinect Fusion and the dataset to the Angular loader, which is our GUI interface. We have another loader with just outputs the results in the console, and you can log them to a file. We can do the same thing with OrbSum as well. And it's all nicely integrated into one framework. So OrbSum's quite a bit faster. You can move around, so do all the things you like. You get some of the stats around here. You can also just load them to a file and also appear over here. And on the other loader, which is console only, we're able to also do it head-to-head. So just have two systems running in parallel on the same data set. So I'll just quickly switch back to this place. Right. So SLAMBench 2 essentially had 4 SLAM implementation with 2 different architectures. We had the same 3 metrics, and we had 6 datasets with trajectory. So at this point, we have a framework that is able to do comparisons on trajectory and is able to figure multiple datasets. And the way it works, and that's what I'm going to show next, is all you have to do to integrate your SLAM system is you have to implement 6 functions, and that gives you access to all the other features, right? So all you need to do is implement those 6 functions, and then you're able to assess the quality of your algorithm on the various benchmarks and datasets that we have integrated. I'll just show that for Kinect Fusion. It's about 200 lines, included as well. So the first thing you have is, say, the new configuration, and in this case, passing a config file. You might be having like any number of parameters that you need to pass to your system. I was trying to just like keep it as compact as possible. But in the new SLAM configuration, all you have to pass is like your hyperparameters. It might be a configuration file, it might be, but you know, like size of your volume or whatever. The next part is initializing the SLAM system. So what you're doing here is you're defining your inputs, as in your sensors. You're defining your outputs. So that might be pose. Usually pose is required. Point cloud sometimes. And then there are a couple of checks you need to do to check to see that your sensors are valid. Allocate some buffers and then configure Kinect Fusion. But basically, at this point, what this function does is you're initializing your system, and that's it. Right. The next bit is the SLAM benchmark will keep sending you poses. We'll keep sending you new frames the way it happens on a real system. So they'll be all decoupled. You'll be getting your RGB frames, your IMU, all the sensors keep firing, and you're getting them with the timestamps, and they're getting sent to your system. And so the way we normally implement this is the system waits until you gather all your various inputs for a full frame. In this case, it's depth and RGB, and it returns true whenever it has both. So the next thing is processing. So here, there's also a phase, so the process bit essentially just is just for timing. But here, all you do is, now that you've gotten your inputs, you're sending it to the SLAM system, it processes it, and we get the timings. And then updating the outputs, you send your outputs to SLAMBench. SLAMBench gathers in the background. SLAMBench gathers all the various statistics that you will later need, and then you just clean your SLAM system. So that's under 200 lines, and you've integrated Kinect Fusion, and you can test it on TOM, ICL, and any other data set. So SLAMBench 3 essentially wanted to go beyond this traditional SLAM paradigm, because, as I said, nowadays we have so many other things such as dynamic reconstruction, semantic segmentation, and also depth estimation, and all of these are starting to be integrated into SLAM systems. And so we felt like a benchmark for these new paradigms is missing. So SLAMBench 3 essentially added these bits with algorithms and data sets. So for semantic reconstruction, we have NYU RGBD and ScanNet, and two algorithms, semantic fusion and OrbSlam CNN. OrbSlam CNN is essentially OrbSlam augmented with a convolution neural network to perform semantic segmentation. And you can see it. So this is exactly the same interface that I showed previously. Again, if you have a new algorithm, it's really easy to compare against this, get all the metrics. Similarly, for depth estimation, so in this case, we integrated an algorithm called Flame, as opposed to many of the depth estimation algorithms. This one doesn't use deep neural networks. It's more of a geometric approach. But again, you can integrate that easily, and you can assess how it works. And the same with non-rigid reconstruction. So here we've added the volume deformed data set. One of the problems that we have, and if anyone's interested in non-rigid reconstruction, this would actually be very useful. There aren't too many data sets for non-rigid reconstruction where sort of SLAM non-rigid reconstruction rather than structured for motion. And so what we've integrated is the volume deformed data set. This data set is essentially a comparison with the volume deformed method because everything was acquired using the volume deformed method. And we've integrated dynamic fusion and we're open sourcing that as well. So the next step for us is, and this was just published last week at ICCP workshop, we want to integrate all these non-traditional SLAM ideas into one framework that we can benchmark using SLAMBench. And so we've developed Full Fusion, and Full Fusion is a framework for reconstructing dynamic scenes semantically. So it's essentially all into one framework. You have non-rigidly deforming models, the static background, and semantic labels, all of them integrated into this one framework. The main idea here was that since semantic labels are something that we think is desirable to have in the scenes anyway, we should use those as priors. They contain important information that we can use. And in this case, we're using that to discriminate between objects that might be static and what might be moving. And so we're essentially splitting the frame into a static frame and dynamic frame, then using the static part to compute the pose. And once we have a reliable pose, we don't have the normal issue with sort of having both a moving camera and moving models in the scene. But what's important about this is that all the various models of this framework can easily be benchmarked using SLAMBench. Right. And so in the future, we still want to expand this framework, but we need to hear from the community, and we really want to see what is necessary. So, as I mentioned at the beginning, lifelong SLAM is definitely one of the directions that we are interested in. OpenLoris is already integrated into that. There are other methods and other data sets that we're interested in integrating. More things for dynamic reconstruction and outdoor environments would be very interesting as well. But at the moment, I think the focus that we are going to have is improving documentation. We feel like that's crucial for a benchmarking framework, and we are still lacking in that area. And we need more community engagement. We need more people to tell us what they need, and we really need to think about like what's the future of benchmarking for robotics. So, as a takeaway, benchmarking doesn't have to be that painful. You don't have to do it like 3 weeks before the deadline and how am I integrating all these various data sets. And you can try it. It's on GitHub. So SLAMBench 2 is still the really stable version. SLAMBench 3 is open source. At the moment, there are all the various branches work, but they're not all integrated into the master. If you did use SLAMBench for the challenge here, for the lifelong SLAM challenge, then we would really want to hear from you and know what your experience was like and know what we should improve.
time for only one question. So if you would like to talk with Mihai, you can talk with him during the coffee break after the next talk. Thank you.